Hello everyone, this is Dr. K. Evangelie Supriya, working as an associate professor in the Department of Humanities and Science, SRIT Engineering College, Andhra Pradesh, India. Today I am going to present you the Engineering Physics syllabus, Unit 1, Wave Optics. So first of all, you should know what do you mean by optics. Optics is a branch of physics that deals with the study of light and its properties. As you can see, what are the properties involved for the optics are, there are geometrical optics. Optics are of three types: geometrical optics, physical optics and quantum optics. So in the geometrical optics, it includes rectilinear propagation of light, reflection and refraction. In the physical optics, it have wave nature of light, interference, diffraction and polarization. In the quantum optics, it has particle nature of light, Crompton effect, photoelectric effect, etc. So the main objective of physical optics is to explain optical phenomena that rise from wave-like nature of light, such as interference, diffraction, polarization, reflection, refraction, which cannot be adequately described by the simpler ray approximation of geometric optics. So it studies light as a wave, focusing on its propagation and interaction with objects, especially those comparable to or smaller than the light's wavelength. Key aspects of the physical optics are wave nature of light, interference, diffraction, polarization, wave propagation. These are some of the properties of the wave. So what do you mean by interference? This occurs when two or more waves meet and combine, resulting in increased or decreased amplitude. So that is called the interference. Change in intensity at the point of superposition is nothing but interference. What do you mean by diffraction? Means that bending of light waves as they pass around obstacle or through openings, a phenomenon essential for understanding how light interacts with the small objects. So diffraction is bending of light ray around the obstacle, around the edges of the obstacle. So this is one of the properties of the wave. Polarization. This refers for the orientation of light waves oscillation and is another wave specific phenomenon explained by physical optics. So another one is wave propagation. It actually provides a framework to understand the transport of light by wave propagation using concepts like Maxwell equations. So there are two types of interference. First of all, the definition for the interference: when two or more waves superimpose on one another, then at the point of superposition there will be a change in the intensity. This is known as interference. There are two types of interference: constructive interference and destructive interference. Now coming to the constructive interference, when crust of one wave falls on crust of another wave, or when trough falls on trough, then at point of superposition then the intensity will be maximum, then it is called the constructive interference. Destructive interference means when crust of one wave falls on troughs of another wave, or when trough falls on crust, then at point of superposition the intensity will be minimum. This is called the destructive interference. As you can see, this is a wave formation of constructive and destructive interference. So there are some conditions for interference. The first condition for the interference is the sources of the waves must be coherent, which means they emit identical waves with a constant phase difference. The second one is the waves should be monochromatic, that means they should be of a single wavelength. Now third one is the distance from the point to one source minus the distance from the point to be the another source. Condition for the constructive interference is equals to delta is equals to n lambda or m lambda, where m or n is any integer. Construction for the destructive interference is equals to delta is equals to n plus 1 by 2 into lambda. So the interference was first observed by the scientist Thomas Young in 1801. How he has discovered means he used sunlight passing through closely spaced slits. It was a difficult experiment since his source was not even close to being monochromatic. But Young's double slit experiment provided the first indisputable evidence of light acting as a wave. So as you can see, the interference condition for the thin film means for the constructive interference, it has m lambda is equals to 2 nd cos beta, and destructive interference m minus 1 by 2 by lambda is equals to 2nd sine theta. So you can see the experimental formation of the Newton rings, because I am going to cover all the topics in the unit 1. This is how the experimental setup. How this Newton rings will be formed means, when a monochromatic light source falls on the glass plate which is inclined at an angle of 45 degrees, then there will be a formation. As you can see, there is a formation of air film between the glass arrangement, where the glass arrangement consists of the plano convex lens and plane glass plate. There the thin film is air film is formed, then the interference will be takes place. How means the intensity in the change in intensity at the point of superposition is nothing but interference. This is how the interference, through the principle of interference, Newton rings will be formed. As you can see this here right side, there is a formation of dark and bright fringes, consecutive dark and bright fringes, where the condition for the bright ring is 2 mu t is equals to n plus 1 by 2 into lambda. Condition for the dark ring is equals to 2 mu t is equals to n lambda. Now, applications for the interference. What are the applications involved for the interference concept means, as it is a property of wave, it is used to determine the wavelength of the light. It is used to find the difference in wavelengths of two spectral lines having small separation from the thickness of transparent, to find the thickness of transparent materials, and to determine the refractive index of transparent solids, liquids and gases, and to find the velocity of light, especially in the Michelson interferometer experiment, and to test the optical flatness of surfaces, and to find the reflecting power of the lens and the prism. Next property of the wave is we are going to study is diffraction. What exactly the diffraction means? Diffraction is defined as a bending of light around the corners of an obstacle or aperture into the region of geometrical shadow of the obstacle. Bending of light around the corners of an obstacle is nothing but diffraction, as it is one of the property of the wave. So as you can see, we can observe the differences between interference and diffraction. It is due to the separation of two waves originated from two different coherent sources. Coming to the diffraction, it is due to the superposition of secondary wavelets originated from the same source. In the interference, bandwidth is equal. In the diffraction, bandwidth decreases as the order increases. In the interference, all the bright fringes will have same intensity. The intensity of bright fringes varies. Now, if for the diffraction, there it is having the Fraunhofer diffraction and Fresnel diffraction. There are two types of diffraction, and we are going to study the Fraunhofer diffraction due to a single slit. As you can see in the Fraunhofer diffraction, the source and the screen are at a infinite distance from the obstacle at the wavefront is plane. Let us consider a parallel beam of monochromatic light of wavelength B incident normally upon a narrow slit AB of width E, where it gets diffraction as shown in the figure below. If a lens L is placed in the path of diffraction beam, a real image of the diffraction pattern is formed on the screen. Let us consider Mn as the screen in the focal plane of the lens. Now, after the corresponding phase difference we will get, and then at the end we will get the intensity. So we can get the condition for minima, where we have alpha is equals to plus r minus n alpha, but alpha is equals to pi e sin theta by lambda, and condition for the maxima we will get alpha is equals to tan alpha. At the end you will know the principal maxima, conditions for minima, conditions for maxima, and conditions for principal maxima. Next, Fraunhofer diffraction due to double slit. Let a parallel beam of monochromatic light of wavelength lambda be incident normally upon two parallel slits AB and CD, each of width B and their separation is D. The distance between the corresponding points of two slits will be B plus D, as shown in the figure 1. So we will get the resultant amplitude A sin alpha by alpha. So after doing all the derivation, we will get the intensity pattern you see equidistant dark and bright fringes. Now, what do you mean by diffraction grating? An arrangement consisting of large number of parallel slits of same width separated by equal opaque spaces. In optics, a diffraction grating is an optical grating with a periodic structure that diffracts light or another type of electromagnetic radiation into several beams traveling in different directions. So, this is a diffraction grating. So grating is an optical device which consists of equal number of parallel widths separated by equal opaque spaces. So the applications of diffraction is also one of the property of the wave. The applications involve the wavelength of spectral lines can be measured by using diffraction grating. The wavelength of X-rays can be determined by X-ray diffraction. The structures of the crystal can be determined by the X-ray diffraction. The velocity of sound in liquids can be determined by using ultrasonic diffraction. The size and shape of the tumors, ulcers, etc. inside the human body can also be assessed by using the ultrasound scanning. Now, coming to the third, as we have studied the properties, interference and the diffraction, the third property we are going to study of the wave is nothing but polarization. So, the polarization in the context of waves like light refers to the restriction of wave oscillations to a specific direction related to the wave's propagation. There are the types of polarization means there are three types of polarization for electromagnetic waves, linear, circular and elliptical. For the linear polarization, the electric field of the wave oscillates along a single line confined to a plane. This plane is often referred to as the plane of polarization. Coming to the circular polarization occurs when two linear components of a wave are perpendicular to each other and have equal amplitudes with a 90-degree phase difference. The electrical field vector traces out a circle as the wave propagates. The third type of the polarization is elliptical polarization, which is similar to the circular polarization, but the amplitudes of two perpendicular linear components are not equal or the phase difference is not exactly 90 degrees. This results in the electric field vector tracing out an ellipse. So next topic we are going to look after is double refraction. Double refraction is also known as birefringence, which is an optical property where a single ray of unpolarized light entering certain materials splits into two rays that travel in different directions. This occurs because the material has the different refractive indices for different light polarization directions. So this is the double refraction. In an amorphous material, suppose consider small n is the same for all polarizations. In some crystalline materials, n depends on the direction of polarization. Polarization of birefringent materials. So there are the ray is split into two rays. One is ordinary ray and extraordinary ray. So in the double refraction, when a light is passing through a calcite crystal or uniaxial crystal, it is splitted into two rays. One is called as a E ray and another one is O ray. E ray is nothing but extraordinary ray. O ray is nothing but ordinary ray. As you can see this, the double refraction was first introduced by the scientist Bartholinus in 1669, where he delivered the two rays of light are each plane polarized by the calcite such that the planes of polarization are mutually perpendicular. For normal incidence, Snell's angle of 0 degrees, the two lines of polarization are also perpendicular to the plane of incidence. For the normal incidence, 0 degrees angle of incidence, Snell's law predicts that the angle of refraction will be 0 degrees. In this case of double refraction of a normal incident ray of light, at least one of the two rays must violate Snell's law, as we know. For calcite, one of the two rays does indeed obey Snell's law, which obeys Snell's law. The ray which obeys Snell's law is nothing but the ordinary ray, which is also known as O ray. The ray which does not obey the Snell's law, which is known as E ray, nothing but extraordinary ray. So for ordinary rays, the vibration direction indicated by the electric vectors in our illustrations is perpendicular by the ray path. For extraordinary rays, the vibration direction is not perpendicular to the ray path. The direction perpendicular to the vibration direction is called the wave normal. Although Snell's law is not satisfied by the ray path for extraordinary rays, it is satisfied by the wave normals of extraordinary rays. In other words, the wave normal direction for the refracted ray is related to the wave normal direction for the incident ray by Snell's law. So this is about the double refraction. So the definition for the double refraction is when a light passing through the uniaxial crystal or calcite crystal, the light is splitted into two rays. One is E ray and another one is O ray. So the ray which obeys the Snell's law is known as ordinary ray. The ray which does not obey the Snell's law is nothing but the extraordinary ray. Next topic we are going to study is Nichols prism. So what exactly the Nichols prism is? The Nichols prism is an optical device that produces plain polarized light from unpolarized light. It was invented by the scientist William Nicol in 1828. That's why it is named as Nichols prism in the remembrance of his scientist. The prism is made of a calcite crystal cut at a specific angle rejoined with Canada balsam, a transparent adhesive. So mainly the principle involved in the Nichols prism is nothing but the double refraction. As I already told, the double refraction means when a uniaxial crystal is when a light is passed through the calcite crystal, it is split into two rays, E ray and O ray. Now in the Nichols prism, as you can see, the prism is made of a calcite crystal cut at a specific angle rejoined with the Canada balsam, which is a transparent adhesive. Now we can see the construction of the Nichols prism. One of the most common forms of the Nichols prism is made by taking a calcite crystal, which is a double refracting crystal with its length 3 times its breadth. It is cut into two halves along the diagonal so that their phase angles must be 72 degrees and 108 degrees. Now the two halves are joined together by an, as I already told, we are in the Nichols prism, a transparent adhesive is used to join the layers, which is known as a Canada balsam. A ray of unpolarized light from a monochromatic source such as sodium vapor lamp is incident on the face AC of the Nichols prism. Double refraction takes place and the ray is split into ordinary ray and extraordinary ray, where the two rays travels with two different velocities. The refractive index of the crystal for the ordinary ray is nothing but 1.658 degrees and the 1.658, and for the extraordinary ray it is 1.486. The refractive index of the Canada balsam is 1.523. Canada balsam does not polarize the light. The ordinary ray is total internally reflected at the layer of the Canada balsam and is prevented from emerging from the other face. The extraordinary ray alone is transmitted through the crystal, which is plain polarized. So as you can see here, the Nichols prism acts as a polarizer and analyzer. Here we will get the E ray and O ray. Now the key applications, what are the key applications involved in the polarization of light means the primary of the Nichols prism. The primary application of a Nichols prism is to produce a plain polarized light from unpolarized light by eliminating the ordinary ray through total internal reflection. That is the first application. Second application is a stress analysis. Engineers uses Nichols prism to analyze polarized light, detecting subtle changes in material structure that indicate stress, which is crucial for developing safer products. And third one is microscopy. Nichols prism were once widely used in mineralogical microscopy to examine the properties of birefringent crystals, and the term crossed nickel still refers for using orthogonally oriented polarizers in this context. The fourth one is polarimetry. They were used to study the properties of crystals that can rotate the plane of polarized light. Fifth one is scientific research. In physics, chemistry and biology, Nichols prisms are essential for studying polarized light phenomena and gaining insights into the internal structure of materials. And the last one is optical instruments. Although often replace the principle of the Nichols prism, has found used in various optical instruments. So the uses of the Nichols prism is it produced plain polarized light and functions as a polarizer. It can also be used to analyze the plain polarized light, that is used as a analyzer. As I already told and shown the figure, the Nichols prism is used as both polarizer and analyzer. So there are some drawbacks for the Nichols prism. So the first drawback includes is about cost. It costs very high due to the scarcity of large and flawless calcite crystals. Second one is due to an extraordinary ray passing obliquely through it. The emergent ray is always displaced a little to one side. The effective field of view is quite limited. Light emerging out of it is not uniformly plane polarized. Now we are going to look at the quarter wave plate and half wave plate. There are two types of plates, quarter wave plate and half wave plate. Now look at the quarter wave plate. If the thickness of the crystal such that it introduces the phase difference is 90 degrees or a path difference of lambda by 4, then it is known as a quarter wave plate. So if the phase difference is lambda by 90 degrees or path difference lambda by 4, then it is known as quarter wave plate. So the principle involved both wave plates, that is quarter wave plate and half wave plate, works by exploiting birefringence. So the thickness T is given by lambda by 4 of mu E minus mu naught, where mu E is the refractive index of the extraordinary ray, mu naught is the refractive index of the ordinary ray. So what are the applications? It is used to produce circularly polarized light. As you can see in the figure, there is a formation of circularly polarized light. If the optic axis of the crystal makes an angle of 45 degrees with the incident beam of light, it is used to produce electrically polarized light if the optic axis of the crystal makes an angle other than the 45 degrees with the incident beam of light. So the next one is half wave plate. So the main difference between the quarter wave plate and the half wave plate is, suppose if the thickness of the crystal plate is such that if the phase difference is lambda by 2, then it is known as a quarter wave plate. So as you can see, the thickness formula T is equals to lambda by 2 of mu naught minus mu E. As you can see in the quarter wave plate, the quarter itself shows, the name itself shows that quarter means 1 by 4. That means the phase difference should be always lambda by 4. As you can see here, the thickness T is equals to lambda by 4 of mu E minus mu naught, and in the half wave plate, the name itself shows that it is half means 1 by 2, such that the thickness of the crystal plate means that T is equals to lambda by 2 of mu naught minus mu E, where mu is the refractive index of the extraordinary ray, mu naught is the refractive index of the ordinary ray. So the applications involved. Another difference you should remember is in the quarter wave plate, it is used to produce circularly polarized light. In the half wave plate, it produces a elliptically polarized light. It produces a phase difference of pi between ordinary and extraordinary light rays. The emergent from a half wave plate is a plane polarized light. It rotates the azimuth of a beam of a plane polarized by 90, provided with the incident angle made an angle of 45 degrees with the optic axis of the half wave plate. So these are the differences between quarter wave plate and the half wave plate. As you can see this, we have covered all the topics in the unit 1, that is wave optics. So what do you mean by wave? And wave means a wave is nothing but a disturbance of the medium. So we have covered the physical optics, like properties of wave, different types of optics and properties of a wave, nature of light, interference, diffraction and polarization. In the interference, we have covered constructive interference and the destructive interference, and the formation of the interference condition for thin films, and then formation of Newton rings. The principle involved in the Newton rings is interference. Change in intensity at the point of superposition is nothing but interference. And we can see the formation of fringes, dark and bright consecutive rings, the condition for the bright ring and the condition for the dark ring. And then we have seen the applications of interference, and second one is diffraction, which is known as bending of light ray around the corners of an obstacle. We have studied the differences between interference and diffraction, and also Fraunhofer diffraction due to single slit, Fraunhofer diffraction due to double slit, and then applications of diffraction. And the third application we have studied the wave is nothing but polarization. Types of polarization we have studied: linear polarization, circular polarization and elliptical polarization. The principle involved is double refraction. And then we have studied the Nichols prism, how Nichols prism will act as an polarizer and an analyzer. And then we have studied the key applications of Nichols prism, uses of Nichols prism, and then drawbacks of Nichols prism. We have studied the differences between quarter wave plate and half wave plate. This is how the unit 1 wave topics is covered. Thank you.